Hello everyone, my name is Ahmed bin Saad. I'm a PhD student in earnest by SimCLR in Paris, France, and I will be presenting a work done with Schlumberger AI Lab in Clamart called Improving Pixel-Level Contrastive Learning by Leveraging Exogenous Depth Information. Contrastive learning-based methods gained a lot of interest lately due to many influential papers such as SimCLR and MoCo and other non-contrastive methods inspired by the same ideas like BYOL. These methods perform well on image-level inference tasks like classification, outperforming supervised baselines because they build image-level representations by contrasting on different sets of transformed images. As a consequence, they are not suited for pixel-level tasks such as semantic segmentation. One proposed solution to fix this issue is PixPro. The idea behind this method is to modify BYOL by adding a pixel-level task that uses the 2G distance between pixel-level features to determine the positive-negative pairs for the loss function. We believe that this method can be further improved. This figure shows a possible failure case where nearby vectors correspond to different objects. To alleviate this problem, we propose PixDepth. The main idea is to leverage the depth information in the pair selection. The image depth does not only provide useful prior semantic information about the correct object boundaries, but also prevents learning fuzzy representations near them. This depth data can come from existing RGBD stereo images or inferred by a monocular depth estimation algorithm such as MIDAS. Here is an overview of the proposed framework. The upper part corresponds to what is already done in PixPro. The lower part shows how we process the depth input exactly as the input used to get the pairwise depth distance. The first mask calculates positive-negative pairs in the image view. We add a second mask that calculates the same thing in the depth view, and the final mask is an element-wise product of the obtained masks. The process of pair selection described depends on two hyperparameters, T and T prime. Objects can come in different shapes and sizes, and this leads to the optimal values of T and T primes being dependent on the pre-training dataset. We want our representations to be aware of the relative context at different scales. We divide the output of our encoder and projector channel-wise into n equal size feature maps, and we independently apply the contrastive loss on each one using different thresholds. We then average all the contributions for the final loss computation. Each byte of the new feature vector will encode a different scale centered around the object of interest. For experiments, we use the ResNet 50 as an encoder to train our method and compare it to PixPro and to the supervised baseline. Performances on segmentation tests are used for this comparison, and different datasets are used for pre-tuning and fine-tuning. All the results and datasets can be found on this paper. In this presentation, we will focus on cityscapes, where we observe an increase on the IOU when we fine-tune the weights obtained by PixDepth. To visually evaluate and compare the quality of the learned representations with PixDepth and PixPro, we propose the setup shown in this figure. We take an input image and we resize it to a large size. We then select a feature vector corresponding to a distant area in the image, and we measure the cosine similarity of this vector with all the other vectors. We can see in these examples that the features belonging to the same objects are more spatially coherent and more contrasted with the background. Thank you for your attention, and I will leave you with a slide of the most important references for this work.